You take a prime number p of the form 4x plus 1, you can always break it into a sum of two perfect square terms. Like you take the number 5, you can write it as the sum of 1 squared plus 2 squared. In the year 1640, Pierre de Fermat found this relation. The prime numbers for which this is true are called Pythagorean primes. For example, 5, 13, 17, and so on. He did not publish a formal proof for this, but in the coming years there were some great explanations trying to generalize this theorem. In the year 1889, Hermann Minkowski, a mathematician and a professor at Zurich, gave a very nice geometrical explanation for this observation. To prove this, we need to know about a fact that for primes that look like this, that is, in the form of p equals 4x plus 1, there exists an integer m such that m squared plus 1 is divisible by p. Let's take the example for p equals 5. Now, while we know this, we will construct a vector space in 2 dimensions. The basis for this is 2 vectors 1, m and 0, p. And all intersection point in the grid are the linear combination of these 2 vectors. That is, this point in the grid can be written as 2 times u and 1 time v. A general point inside this grid is of the form a, times m plus b times p. If we calculate the distance of any intersection point from the origin, then we write it as a squared times 1 plus m squared plus p times this polynomial. 1 plus m squared is a multiple of p, as mentioned earlier. So we can prove that the square of distance of any of the points in this grid is of the form n times p. If you calculate the area of any one parallelogram, then we get exactly p. Now, if you draw a convex symmetric shape with area greater than 4 times the tile area, let's say a circle of radius root 2p, it will contain at least one non-zero vector w. For the closest point to the origin, it should always lie inside the circle. We suppose its coordinate to be x, y. The distance squared for this point should be equal to p, as it lies inside the circle, and its radius square is 2p. And we can write the expression as x squared plus y squared equals p. Here, x and y are integers, as the basis to form this grid were also integers. The equation becomes x squared plus y squared equals p. This proves our theorem. By shifting our gaze from abstract algebra to the physical geometry of the grid, we say that the secrets of prime numbers are often hidden in the patterns of the space they inhabit. Consider subscribing if you learned something new today. Thank you for watching.